This is a video for AQA Discrete Mathematics. It's Game Theory section 1.1, where we're introducing the idea of game theory and looking at payoff matrices and play-safe strategies. Well, in simple terms, game theory is about decision making, where different people have possibility of different strategies, and we want to decide, or they want to decide, which are the best strategies that they should employ in any particular situation. The idea, specifically, if we were to word it mathematically, is the study of mathematical models of conflict and cooperation between intelligent, rational decision makers. You don't really need to know that as a definition, but it gives you an idea of the sort of level of things we're talking about. The idea of a rational decision maker is one who literally isn't rational, so will always take best choices at any particular time. It's used in economics, political science, or name a couple, and many other areas where there are decisions to be made and we have two or more people. It's to do with deductive reasoning, trying to avoid worst case scenarios, and possibly collaborating and trying to outsmart each other. So a lot of intrigue in there mainly, or maybe. Well, one simple example of a game theory, literally a game in this case, is rock, paper, scissors. I'm sure you're familiar with. This is what we call a two-player zero-sum game. And the two-player, pretty obvious, there are two people involved. The idea of zero-sum is that one person's gain is equal to the other person's loss, so that in total the gain is equal to zero at all stages, whatever happens. So two players, only two people can play. A zero-sum, where the gain and losses cancel each other out. So in that particular case, there's no point in collaborating, because if you collaborate with me and I win, you necessarily lose the same amount. The gains and losses are shown in what we call a payoff matrix, and this is literally that, showing the outcomes of using the different strategies available to the players. Now, a payoff matrix is usually given in terms of one of the players. Here we've got two players, player 1 and player 2, so invariably the payoff matrix will be given in terms of player 1. So if we take plus as being a win, so +1 as being a win, -1 is therefore losing, and 0 being a draw, then the payoff matrix for this would read as follows. This is player 1's payoff. Be a draw if we both choose rock. I'm going to lose if I choose rock and you paper, but I will win if I choose rock and you scissors. And we can keep going like that. If I choose paper and you choose rock, then I win. If we both choose paper, it's a draw, and if you choose scissors, you win. And finally, if I choose scissors, I'm going to lose if you choose rock, but I will win if you choose paper, and it will be a draw if we both choose scissors. So there's a very simple idea of a payoff matrix. Notice that the payoff matrix here is done for player 1. If you wanted to look at the gains to player 2, you would have to negate this. Everything would be just minus. So this is always going to be the case, that we look at the winnings from the point of view of player 1. So here's a different game. This time we're just looking at the gains to Sue. And she has got two strategies she can play, A and B, whereas Jim has got different strategies, X and Y. And we could ask questions about this then. For example, what is the outcome if Sue plays A and Jim plays X? Well, clearly we can see there, if Sue is playing this one and Jim this one, then the outcome would be that Sue will win 3 units, whatever those units might be. We might ask then, what's the worst that could happen for Sue if she plays strategy A? Well, if she plays A, we can see that the worst that she's going to be is given by this value here, the -2, and so she will be having a loss of 2 units to Sue. Of course, if she loses 2, then Jim has necessarily won 2. What's called a play-safe strategy is one where we try and minimize the risk, if you can think of it like that. So both players will try and make their potential losses as small as possible. So remembering that this is the payoff matrix for Sue, then the worst that can happen to Sue, as we've already discussed if she plays A, is -2. So we look here at putting in the row minimum. So the row minimum here is -2 for Sue if she plays A, and if she plays B, the worst that can happen is that she has 0, so she neither gains nor loses. So Sue's worst potential loss, -2 and 0. So her play safe strategy is the one which makes that potential loss as is the largest value. So these are the minimum values giving you the loss. We want the largest of those, so that will give you the smallest loss, if that makes sense. So her play safe strategy is the what's called the row maxi min. So the maximum of those minimum values is given by the 0 that is there. Jim, on the other hand, he's going to get his potential losses by looking at the maximum. The worst that can happen to Jim is if we get the 3 there, because Jim is going to lose 3. So look, we're looking for Jim at maximum values, and if he plays Y, the worst that can happen is the 1 there, he loses 1. Now he wants to make his potential losses as small as possible, so his play safe is here playing Y, where he loses 1. So the play safe strategy is going to be the row maxi min for player 1, or Sue in this case, and the column mini maxed for player 2. And that's because, as I say, the values in the payoff matrix are given from Sue's perspective. So she wants to make her the smallest value as large as possible, whereas Jim wants to make the largest value as small as possible. So those are the values that we found in the last slide. We can say therefore that Sue's play safe strategy is B, and Jim's play safe strategy was Y. Right, let's look at this situation then, which is a different payoff matrix. So to work out for player 1, we need to look at the row minimum, and we can work those out very easily: -1, -2 and -3. And so the play safe is given by the row maxi min, and that is equal to -1, giving player 1's play safe strategy as P. The column maximum values that we need to look at for player 2, those are -1, 2 and 3, and so for player 2 we want the column mini max, so the column mini max, and that's equal to the -1, giving a play safe strategy for player 2 as X. That means that if player 1 plays P and player 2 plays X, player 1 is going to lose 1 unit and player 2 gain 1 unit. Now, if player 1 knows that player 2 is going to play safe, then say, well, is there any advantage in them changing their decision? So player 1 can say, let's assume that player 2 is playing X, and can look down the column for X and say, can I gain anything by changing? And player 1 will look at this and say, well, no, there's no point me changing to Q because I'd be worse off. And likewise, if I change to R, I'll be worse off. Player 2 is looking at the same thing in the other way around and saying, what would happen if I change from X to Y or Z? If I think that player 1 is going to play P all the time, should I change to X or Z? From X to Y or Z? And player 2 look at that and say, well, no, if I change to Y, I'm going to be worse off with just a 0 game. And if I change to Z, I'm actually going to lose 1 instead of winning 1. So there's absolutely no point in either player changing. And this is what we call a stable solution. Here's a slightly different scenario. And here we have row minimum. So these are the minimum values in the row of -2, -1 and -2. So the maxi-min value is equal to -1, giving a play safe this time for player 1 of Q. The column maximum values are equal to 3, 4 and 2, giving a column mini-max, so column mini-max equal to 2, and therefore a play-safe strategy for player 2 of Z. Now if they do that, then there's 0 to either of them, a draw if you like. So let's go through that. What happens if scenario? What happens if player 1 knows that player 2 will play safe? So player 1's looking at it and saying, I'm going to play Q, and if player 2 plays Z, we both gain 0. But player 1 thinks, if I switch to R, I could gain 2. So it might be better for me to switch. Player 2 is looking at the same thing and saying, I'm playing Z at the moment and getting 0, but if I was to switch to Y, I would gain 1 instead of losing. Or, knowing that player 1 might change, player 1 might change to R, so if that happens and I happened at the same time to switch to X, we might end up here. So player 2 would then gain 2 units. So we have here what's called an unstable situation, where there's some gain to be made by changing from the play safe strategy for each player. So then we have to decide how to go about, how often do we swap. So this is termed an unstable situation. Well, that's the end of this introduction to game theory. In the next 2 videos we'll look at those situations, the stable solutions and the unstable, where we have to produce what's called a mixed strategy. So in the next video we'll look specifically at stable solutions and an idea of what's called dominance.